Explosure!
And what I'm going to do today is I'm going to go through some of the areas of physics. I just wrote them down on the board because I'm going to give you an exam afterwards. And there are two kind of basic overarching areas of physics. One is called classical physics, and that's more or less everything before 1900. And then there's modern physics, and that doesn't feel very modern to you right now, but it's kind of everything after, a lot of things after 1900. And what we're going to do today is I'm going to go through some demonstrations that cover three of the areas of classical physics. That is mechanics. Mechanics is how things move. Then thermodynamics, thermo, heat. This is about heat and things relating to heat and pressure and things like that. And the last area is electricity and magnetism. I have here a bucket of water. It really is a bucket of water, I'm telling you the truth. All right? So if I take this bucket of water, and your camera is not too expensive, right? Right. Just an iPhone. And it's an iPhone? Forget it, I'm not going to do it. That's precious. This camera's not too expensive. All right? And I throw it this way. Do you guys kind of know what's going to happen? Yeah. Water is going to go somewhere. But in this case, I'm going to throw it this way because it's not really nice to get people wet, other than myself. So here we go. Ready? You guys ready? So now, as long as, you know, one of these days this handle's going to break off when I'm doing it. As long as I keep moving this, it stays in the bucket. And the reason for that is one of Newton's laws of motion. And I have to tell you, if I stopped it above my head, what would happen? Exactly, the ball problem again. Gravity would pull it down on my head. But one of Newton's laws of motion says something moving wants to keep moving in a straight line. And I have to apply a force to make it turn. And so therefore, it's the force on the bottom of the bucket that keeps it in the bucket because it wants to go straight. And that's the reason it doesn't fall out when it's over my head as long as it's moving. But if I stop it moving, gravity takes over and I take a bath. All right, so here I have my momentum balls. And if I pull one up on this side, how many people think on this side 4 are going to go up? Raise your hand. How many people 3? How many people 2? Multiple voting. How many people 1? Oh, excellent. So this is a demonstration of something called conservation of energy and motion. That is those are two of the most important subjects or laws in mechanics. Okay, so very good. If I do 2 on this side, how many people think 1 on that side? How many people think 2? How many people think 3? 4? 5? Okay. The 2s take it again, and we still have a double voter. Okay, so now this is excellent. Now we've got a problem. I've got 5 balls. What? I'm going to do 3. I only have 2 left. How many people think 2? How many people think 3? How many people think 4? How many people think 5? All right, let's go. Here we go. Now this is cool because one of them is actually getting transferred back and forth. And that's because this type of collision conserves momentum and energy. And so that's what has to happen. The way a rocket flies is simple. You put water in it, and then someone gets a pump and pumps it up. So in reality, you don't put water in it, but you do put something like water in it. You put hydrogen and oxygen, which is water. And then what happens is in the real rocket ship, you put them together and ignite them, burn them. When things get hot, what happens? Do they expand or contract? Expand. So they expand, they push out the tail, which is actually out of the nozzles in the back. And when they push the gas, the hot gas that way, conservation of momentum says the rocket ship has to go this way. And so cover your iPhones. All right? Good catch. Excellent. Can you all see the vortex in there? The vortex is that swirly whirlpool. This is sometimes called a tornado bottle or tornado tube. The basic idea is the same as how a tornado works. You look at it and you say, this is cool. But here's the amazing thing. We do not understand all the physics of this. If you look at this, so I'm going to turn it over again. And by the way, if I do this carefully enough, this blub 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 will stop and there you go. And it'll just sit there, even though there's an opening. It's actually the surface tension of the little opening that is holding it and not allowing the water to fall down, which is kind of cool. But if I give it a spin, the air will come up in the middle, and there we go. All right, now I'm going to take this. It really and truly is blowing out. But when I stick this in, it actually holds it in. So let's think about that for a second. Very short second, actually. And the second that I'm going to think about it is when the air spreads out, do you think it goes faster or slower when it spreads? Slower. Very good. It goes slower. So in the neck of the funnel, that's back in here, the air is faster than out here. Remember what I said, the pressure is lower where the speed is higher. So in the throat of this, the pressure is actually lower. So even though the air is coming out, it's actually pulling the ball in. And what I can do is if I hold it above this, it'll do the normal thing. It's only when I push it down into the funnel that the pressure difference occurs. My hand is really hot compared to this. How many of you have ever put a little bit of water on a hot frying pan? Good. You know what happens if it's a really hot frying pan? It doesn't just boil away. It bounces, it makes little balls and bounces around. Have you seen that? Yeah. It's called the Leidenfrost effect. And what happens is a little layer of vapor forms under the ball of water. And the same thing happens if I pour a little bit of this on my hand. It just rolls right off my hand. Now notice something, I'm not making a cup out of my hand. That wouldn't feel good. And it would badly frostbite me very, very quickly. And that's one of the reasons that I don't like doing this with a Band-Aid, because it can get caught on the Band-Aid. And in fact, one time I was pouring some on a table to show people the Leidenfrost effect, and what it did is it poured onto my pants. And pants act like a sponge. And I did a dance. There are waves in air, and one of the ways we can make these waves is by making our very own organ pipe. You guys have blown across a bottle and made a sound? Yeah. Okay, that is an enormous flame. Okay, I hope I'm not going to melt this. Catch the room on fire. What's happening is an oscillation, a pressure oscillation, is being set up in here by the rising air from that flame, and that's what's actually making the sound. All right, ready? Here we go. 1, 2, 3. Whoa. Whoa. So what happened was the electricity ran around through that wire. And when it ran around through that wire, it made a really strong magnetic field called an electromagnet. That electromagnet actually made a current flow, an electrical current flow in that can. And those currents the magnetic field pressed against that current, and that collapsed. Physics is all around you. All you guys have to do to be scientists, physicists or other types of scientists, is simply look around and ask questions and be curious about how the world works. And that's what scientists do. Have a great week or 10 days or whatever.